All right, so let's get back to our root finding methods. This is going to be the part 3 of the lecture 5 on root finding methods. So we have seen so far 2 different methods. One of them was a bisection method and another one false position method. And let's just, this slide has nice graphics on bisection method. So essential idea, bisection method is a bracketing method. Therefore, you need a bracket where your root is. Okay? So once you have an idea, and you might know that because you know your function or you know your data, so you sort of approximately know where to search for the root. And when you do, okay, then you essentially, let's say that here in this particular case, we have 12 and 16 as the bracket. Then you will simply halve that interval into parts. So basically the half is here at 14. So after we have 14, so one crucial part about the bracket is that function is positive at one side of the bracket and negative at the other. Okay? So when you multiply f of what's the lower part of the bracket times f of the upper part of the bracket, you're going to have a negative number. And then you know essentially if the function is continuous, well, somewhere in between, I have to hit a 0 if I'm going from a positive to a negative number or from negative to a positive number. So then my choice of the next bracket is once I halve the interval, I'm going to actually, okay, so this is my half. Between the two choices, I could go here or I could go here. Now, obviously, here I actually have a visual, so I say, well, obviously, this half of the interval is the correct one to go next. But if I didn't see that interval, what I would check is again this criterion that I have a positive and a negative value at the ends of the bracket. So I basically maintain the bracket as I halve the interval. And then on the next go, okay, so now 14, 16 is my choice. Next half is 15. And basically, again, visually, I see that I should stay here between 14 and 15, right? 14 and 15. However, what I'm going to actually check is that f of 14 times f of 15 is a negative number, and that's the bracket that I keep, and I keep going. Okay? So this is something that we implemented 2 times ago now in class, and last time, actually, we modified it to a so-called false position method. So this bisection method, it really, if you have a bracket, it will work. It might get there very slowly, but it will work. So if you have time, you will actually find a solution. However, now we're always wondering how I could improve and how I can speed up in cases where things don't work. And my Facebook is annoying. So essentially, one of the improvements, possible improvements in some cases, is false position method. And what that method does, says, all right, well, I have my bracket that has 2 sides. Let me actually, I have my bracket that has 2 sides. So essentially, this is my lower and this is my upper end. And technically, I'm always halving, so I'm always going straight in between. What if I try to actually get closer to the actual root by estimating which one of these ends, L or XL or XU, is actually closer to the actual root, so try to get closer to it instead of just halving. And one way to do that, or get sort of a linear estimate to it, is essentially, okay, I don't know what necessarily my function is and where the root is, because if I knew I wouldn't be searching for it, but I can approximate this function as a linear function in between these 2 points. Okay? And then I'm going to search for this point where this linear approximation to my function intersects the line y is equal to 0. And that's my, I'm hoping, better estimate for the root. Okay? So I'm going to, instead of halving this, so having my xr right in the middle there, I'm actually going to go for this estimate. And this estimate I can actually get from geometry. So geometrically, these two triangles are similar. If they're similar, then f of xl divided by this length of here, which is xr minus xl, this is this side, is equal to f of xu, which is this length here, divided by the length of this side. Okay, so basically from that, I can estimate what xr is. So my xr is, when I solve it, equals to xu minus f of xu times xl minus xu divided by f of xl minus f of xu. So this is basically a one-line change to my bisection code, and I'm gonna show you. Can somebody briefly check? I think I posted bisection.m in files/MATLAB on Canvas, but if not, I'm going to correct that. But let me just show you the code. So let's just quickly go over the code that we put together last time. So first there was this function f, and I have f of x coded as this is basically a cubic function of x. So I have it coded. So if I type in f of x, it's in the same directory as my bisection.m. So first we were plotting it and sort of looking for where it is that I could actually. So if I execute that, just this portion. I'm actually just gonna, okay, this is a standard problem I'm having when my MATLAB is open before projector comes into the picture. So apparently I have to always open MATLAB after I hook up my computer to projector. Okay. So let me just try, So this first portion just plots the function, and if you remember, this is the function that actually has 3 roots. There is one between 4 and 5, there's one between 0 and 2, and there's another between -1 and 0. Okay? So if you actually go, so this is the first part, I'm just plotting to actually find the bracket. Now, basically, I then choose the bracket, so I say, okay, 4 and 5 is my bracket, so my starting left and upper points are 4 and 5. And I'm just here remembering them because they will get overwritten. And I set my iteration counter to 1, and essentially I immediately compute what is my current relative error. It's when I don't know what my root is, I'm using my last 2 iterations essentially as my error measure. So I'm going to take absolute value between xu and xl divided by absolute value of xu. Basically, I'm behaving that I'm pretending that xu is my current best estimate for my relative error, for my true value of the root. Okay. So since I don't have it, this is what I do. So this is my relative error that I'm measuring. And I keep going. I say, okay, this was actually a test, so I'm going to remove this for now. So I'm going to say, while my relative error is larger than some cutoff value, which cutoff value, that depends on the problem you're solving. If you don't have an idea, well, then you try it out and see how it works. Typically, if you're actually, this is a problem where I have a cubic function that is, I just came up with it, okay? So I don't have a physical context of the problem I'm solving. Typically, there are certain things that come from the physical context. So if I'm actually fitting some measurements, some physical measurements, and I know that my measurements are accurate to the second digit after 0, well, then obviously going to the relative error to be 0.000005 doesn't really make sense if my measurements or the numbers I'm working with are not very accurate themselves. Okay, so you're gonna tune that based on the problem. And I could also, so this is something that I had here, and my iteration counter is less than, let's say that I can say I want to stop at 1,000. So just in case I hit the problem and I don't want this loop to go on forever. But these are a little dangerous because 1,000 is arbitrary. Okay. So this is again up to you. So I'm gonna actually put this note here. Note that maximum iteration count of 1,000 is arbitrary. And then I'm going to increase the counter, and basically I'm just going to, my bisection choice is just halve this interval. Okay? And if my f of xr, this new choice times f of xl is less than 0, then let this upper value become xr, because xl, xr is a good choice of a bracket in the next step. Otherwise, my xl is xr. And this is essentially what I keep going in the while loop. I will just reevaluate the relative error, and I will keep going. So I'm actually remembering relative error as I go, so I can plot it at the end. So after this, I'm going to turn off this plot. If 0 is a very easy way to turn off a plot, because, well, it's not going to execute. So then after this, I'm just going to plot the relative error. So this is essentially how it looks like. This is the function as it is. My approximate root is 4.6718 and so forth. Relative error fell below 0.005 as requested, and it did so in 7 iterations. I can plot my relative error. I'm plotting the logarithm 10, so that way I actually see better, because at some point as the relative error goes below, say, 0.01, they're all going to look on top of each other, and you're not going to see the difference unless you actually plot the logarithm of the error. So you can see that it's going down. Now, what would false position do? So for false position, I would basically just change this root choice to be this xu minus f of xu times xl minus xu divided by f of xl minus f of xu. And actually see whether it works better. That is not guaranteed. I think last time we executed it, we didn't get a better behavior. So I actually have 19 iterations. My relative error ultimately went down, but for a while it was hanging at a pretty much similar value before falling down. And this is likely, now this is my guess, because I'm trying to estimate something. This is basically possibly here we got so close here that halving the interval and choosing this supposedly better choice doesn't really give me much leverage. This function kind of looks like a linear function in the neighborhood of this point. So probably the trade-off or the benefit of using false position is not much, and actually here I'm actually not going to get a faster convergence. So there are always, even though in general this is sort of the rule that bisection errors do not go down as quickly as false position, you can always find a counter example. And there are always pitfalls like that. Yes?
Right, so you're saying for the false position method that it only works when the two ratios are equal to each other? Is that the premise?
No, I'm just saying that probably here two ratios are very similar, so basically between bisection and false position, there is no clear benefit of false position or the other. Basically what happens here is you're betting on this. This is a linear estimate of the function, of the actual function. And you're betting that if you take the linear estimate of this function and you're finding the root of that linear estimate, which is linearization of the function in the neighborhood of the root, Okay? You're betting that this point will be closer to the actual root than just halving this interval. Well, that might or might not be true. So for false position to work faster, that actually has to be consistently true as you're iterating. And that's essentially. So again, these are sort of certain tricks that you're trying to do for, in a general setting. Unless you precisely know what f is, you don't always know the precise behavior of the function. So you cannot really find a generally working or the function, the root finding method that works always. And that's the theme that we are actually going to have in this lecture. And this is why we will actually learn something of the order of 5 or 6 different methods, because you have to have choices. Okay. So nothing works ever perfectly, so you have to have choices. So this is actually an extreme example. This function is x to the 10 minus 1. Now, I didn't really need a method to tell me that 1 is actually a root of this, okay? But if you actually did this, so if you actually did it on the interval between 1 and, well, let's say approximately 1.3, okay? If we actually did the search, then this linearization of this function is actually really far away from the actual function. And because it's really far away, it's not going to help me in estimating the root better. Yes?
Can you explain what replacement we're making when we run the false position method?
So here, in this particular function, my next choice, that xr, would be simply half of this. So I would be here. Okay? So instead of, so my bracket started as 0 and 1.3, and my next choice would be here.
So why
Okay?
the purple line's not going?
And now this line, this first line, like right here, would be the choice of the false position. And that's obviously further away than the actual root. So it's not helping me. Okay? And then I keep going and I keep doing the same, so false position will take longer. Okay? If we want to quickly test that, I can modify this particular code. I'm going to modify this f to be y is equal to x to the 10 minus 1. And I'm going to ignore this plotting of the function, so I don't, because I have it plotted, so I don't need that. So I'm going to ignore that part. And I'm going to say, okay, this is 0 and 1.3. So let's see what bisection does. I hope I didn't make any other. Okay, this is now bisection. So my bisection did it in, so I'm fairly close to 1. I'm definitely close within 0.005%, or rather that was 0.5%, which I'm here at 0.3%, fine. So number of iteration was 10 for bisection. Let's see what does false position do. So this is 10 iterations and I was done. Here I actually went to 1,000 and my relative error still stayed large. So this is a very extreme case of false position not working. So I actually hit here my number of iterations. That counter was a good thing to stop me from iterating endlessly, because I'm obviously not getting better. Let's actually see what happens if I don't have this iteration count, maximum iteration count. Do I get an infinite loop? I don't know. I'm gonna test it right now. Yep, it seems that it keeps going. So having that maximum iteration count can help in certain cases where you just hit a very bad. So let's see, Control C, Control D, Control C. All right. So I obviously my iteration count went up to this. Okay. So it is good to have actually. I'm gonna put it back here. And maybe not 10, but let's give it at least 10,000, right? There we go. So now that will actually, so I see even if I let it go to 10,000, my relative error didn't improve. Okay? All right. Okay. Now, so basically in summary for bracketing methods, I do need to kind of estimate where my function is, or typically we look at the function graphically and figure out what the bracket should be, or maybe I know something about the physical behavior of the problem that tells me where I should search. And then once I have this bracket, where bracket means that my f of the lower end times f of the upper end is negative, then I can actually employ either bisection method or false position, and I will find the root. Now, in this case of false position, my relative error might not go as much down as I would like it to go. So there are always some pitfalls in these methods, but we need to actually go and keep searching for different methods. One thing that does bother me with the bracketing methods is that I have to have a bracket. Why can't I just start from a guess and keep going, keep searching? Okay? So what would that be? So let's actually see open methods that require only one guess. So those are usually faster, but again, nothing really guarantees me convergence, and we'll see the examples of that. So one of the such methods is called fixed point iteration method. Okay? And the way it works is that, okay, possibly in certain cases, I have an equation that I can manipulate such that I can, so my original equation was f of x is equal to 0. Okay? Can I manipulate that into a form that x is equal to something else? So my original root finding equation where I basically equated something to 0, let me rearrange that and put x on the left hand side and everything else on the right hand side, and let's see whether that works. So for instance, if I have 4x squared minus x plus 3, okay, then one choice would be actually to say, okay, x equals to 4x squared plus 3. Okay? So I have it in this form, x is equal to g of x. If I only had sine x is equal to 0, well, that's a little more difficult. There's no x is equal to, well, I can always add x on the right hand side. So x is equal to sine x plus x. That works too, maybe. We'll see. So now that I have it in this form, the idea is to start with a value x0, and then from there, your next choice is g of x0, that's your x1. Then on the next choice, you go with g of x2, and so forth. Okay? And you sort of iteratively update this x, and you're hoping that you're going to get closer to the root. So the problem with this is obviously there might be some different ways to rearrange this equation, and we'll see that the things, some ways will work and some ways don't work. And some of these basically diverge, they get away from the root. So for instance, one thing, so what I'm really looking for in these equations is that I'm looking for this g of x, I'm looking for the intersection between y is equal to x, this is my y is equal to x, and this function g of x. So I'm looking for the intersection of this. Now here are some examples where it works and examples where it doesn't work. So for instance, in this particular case, this is my plot of y is equal to x, or function y is equal to x. And this is the plot of this g of x. And I'm essentially looking for this intersection. So the way we start is we pick an x0. It's right here. Okay? After I pick an x0, I evaluate g of x0. Okay? So this is the way I'm iterating. g of x 0, its value is right here. Okay, this is the function g of x. Now, what I'm actually going to actually go further, I step over to this function. This is a plot of a function where both my x and y values are always equal. So my x1 is actually right here. Okay. So now for this x1, I'm going to find g of x1. That's my x2. Okay. So this is g of x1. I walk myself over to this function where y's and x's are equal, and I find its x value. That's my actually x2. And I keep going like this. So I can see that actually here I'm kind of like sliding down this route, this intersection point. So I will actually get closer. Now let's see an example where that's not the case. So let's see actually this particular one. So I start, this is my function g of x, and this is my function y is equal to x. So my x0, I get to g of x0, okay? This is g of x0, this value here. Now if I walk myself over to this function y is equal to x, its y value is the same as this, but its x value has to be the same as y value. So this is my x1, okay? For this x1, I find g of x1, that's my x2, okay? I again go to this y is equal to x and find the intersection, so this is my x2. I will actually here spiral outward, and I'm getting away from this intersection, I'm not getting closer to it. And there is actually a rule, so this particular method will converge on the given interval only if g prime of x is less than 1. If it's not, I'm going to spiral outward and I will not find it, even though the route actually exists somewhere nearby.
Good question. Okay, so for part D, like you guessed x naught, right?
Mhm.
And then, okay, so then that horizontal line, that's the horizontal line between right.
So this value is my g of x0, right? So my x1 is actually g of x0.
Okay.
So for this value, this y is this value. I go to this function y is equal to x. So this point, okay, has both y and x value equal to this much, which is g of x0.
Okay.
So its x value is my x1.
Okay.
Because y and x value are equal on this line.
Okay, so then.
Right? So then for this value, I'm finding my g of x1, which is now this much. So that's my g of x1, that's my x2.
Right.
Okay? To actually find it graphically, so basically this value, I just go to this is for the same y value, okay? I find this point on y is equal to x. It's right here, okay? So for this y is equal to x, both of its y value and x value have to be equal, because that's the function is y is equal to x. So therefore my x2 is right here. And I keep doing it. So now I would actually go probably somewhere down here for my g of x2, right? All the way down. I don't know how this. And I would basically spiral upwards away from this.
Okay, and then when you're seeing when like g prime of x is between 0 and 1, what are we plugging in for x to check that? Like what would we
So basically I have in mind with starting x0 somewhere in some interval. So for that interval, somewhere around this x0 that I'm starting, I'm calling that interval A and B. For that interval, I have to have my g prime values in absolute value less than 1. And then it will have a guaranteed. So it's a very narrow, I have to find this x is equal to g of x. But also the actual value that I'm looking for is not necessarily going to work. So let's go back here, okay? So if I'm going to work x is equal to 4x squared plus 3, my g of x is 4x squared plus 3. What is g prime of x? 8x, right? That's simple, I can compute that. It's a polynomial. So 8x, and if I start around x0, that is 2, let's say between 1 and 3. Okay? 8x on interval between 1 and 3 will be between 8 and 24. That is not less than 1. Ain't gonna work. So starting with x0, which is 2, is not gonna work. Because around that neighborhood of 2, I have g prime of x that is larger, much larger than 1. Okay? So this is actually nice, very nice rearrangement. It's not gonna work on now, what are the actual solutions? So maybe I can find, if I go to somewhere like 0.01 to 0.05, somewhere there, 8x should be fine. So if I go to smaller values of x0, I should be okay. So again, on the given interval that I'm looking for, I should be finding. Now that said, this is a quadratic function, so we can actually just use an analytical formula. Okay? All right. So again, it's not a given that I will have convergence, but this is one of the possible methods. Fourth method that we're actually going to introduce is Newton's method, or so-called Newton-Raphson. And this method, xi plus 1 is basically, so the formula is given up there. What we're really doing is the following. So these are my current iterate xi, and this is my function in blue here. Okay. So this function says, well, let me check out the slope of the function. Okay, and slope of this function is given in black here. So here for the next choice of next iterate xi plus 1, how about I just kind of slide down this slope and see where I hit 0. That's going to be my xi plus 1. So this is another way to sort of like semi-linearize the function and try to get to the root. Now my root in this particular case is here, and this is actually getting me closer. And on multiple number of iterations, this might work better than any other method, because depending on how I chose my bracket and bisection, I might be very far away. So this method, if I actually now, I know that f prime of xi is essentially, so here I have value f of xi. So this length here is f of xi. This length here is xi minus xi plus 1. Okay? So that's basically going to give me my slope estimate, and from that I can actually compute what xi plus 1 should be. Okay? So it's essentially calculation from this triangle. And that's essentially where this formula comes when you actually solve this. Xi plus 1 is equal to xi minus f of xi divided by f prime of xi. This works well if you actually have a function f and you know what f prime is, so you can actually plug it in. And when it converges, it's some of the best convergence we see. It's quadratic convergence. However, it doesn't always converge, and there is no guarantee where it actually converges. You can also derive the formula multiple ways. It can also be derived from Taylor series by chopping off all of the quadratic terms. So here are some examples or some pitfalls where it doesn't work. So if I have any kind of inflection point, this is an inflection point, where I have essentially a sudden, so f double prime of x is equal to 0. So my f prime of x changes sign. Okay? So I'm going from negative to positive f prime, or the other way around. In those cases, we're actually not going to see convergence of this method, because I will be constantly sent sort of on the other side and away from the root. So we can actually then second problem is that if I actually have sort of a local minimum is where my f prime is close to 0, and that can cause trouble, so I could start oscillating back and forth between method without ever really going to this root. So basically, this root is there is a bunch of what you could say peaks and valleys in between the starting point and actual root. So when that happens, then we have trouble. Okay? So for a Newton method to work really well, I should be sort of on the same side of the mountain as my root when I start. And then I will slide down to that root really closely, so right here. Okay, this is what I call on the same side of the mountain. If I have this peak, which is a maximum, and my x0 is actually on the other side of the mountain, my iteration will send me away from the root and not closer to it. Now, I might have another root somewhere here, so I might hit a root, okay, but not this one over here that I'm trying to find with this iteration. Okay? So again, there is no, in any kind of zero slope when you actually precisely hit the peak or the valley, where you actually have f prime being a zero, that is sort of a disaster for the function because you can't divide with a zero. So it really depends on the nature of the function. So often you will guess and you will try multiple methods and until you actually find solutions. All right. So secant method is just, and this is basically, I think, well, next to last method we will mention in this lineup of methods is basically, okay, I might not know what my f prime of xi is because I might be using data and not the function. And in that case, I might simply replace f prime with an estimate to it. An estimate to it is f of xi minus 1 minus f of xi divided by xi minus 1 minus xi. So this is basically just the slope near these two last points that we're using. So basically, instead of using actual here, actual tangent right here to this blue line, I'm actually just gonna do this line instead, which is the slope of the line at this last previous steps, and that gives me another way. Now, by now you're probably getting dizzy. Oh my God, there are all these formulas that I'm shoving down your throat. But essentially, the iteration is not that difficult. If you have the formula, all you need is really to program this is you need a rule. How do I get my next iterate? So I need an initial guess. I start from some x0. And then I need to start iterating. So let's actually go and give it a shot. Okay, let's actually go and program. And you can either, well, let's actually give you a pick. We can either work with some of these difficult choices here that I used at the very beginning as examples, or we can use that cubic function that I showed at the beginning of the class. Which one would you like to work on? Peng-Robinson. All right, there's a choice here, Peng-Robinson. Is there any other preferences? So program this function, okay? We can actually, so this is basically the Peng-Robinson. And I'm actually going to go to the slide where we worked on it. There we go. This is my Peng-Robinson. So program this function f, and then let's choose a method, one of these latest choices. Play with it a little and see whether there is a nice way to arrange this function to have this x is equal to g of x, or in this case, vi is equal to some g of vi. Okay. So try to find a fixed point iteration method, and for now work on the paper as well as using your sheet, and see where you get. And if you don't converge with the fixed point iteration, try to see why you don't converge. and then move on to using Newton's method. So let's start that now, and we will work on it some next time. So did everybody write this down, or do you have them on the slides? Or rather, is it better for you to have the view of the function or view of those methods that I'm suggesting? Methods? So you have this written down, I hope. So here's a fixed point iteration. And this is Newton's. We have a file with all of them. So here's Newton-Raphson. Here I have everything on the same slide now. So this is the Peng-Robinson. So again, you need to start with x0 and iterate from then on, and hopefully those iterations converge.
And you wanted us to just do fixed point, or?
I want you to compare fixed point and Newton-Raphson, and there will be a little bit of searching. What do I start from? What is my starting V, VI?
So which of the
So I don't know now from the top of my head. I don't know how ugly or pretty this graph is. And obviously you gotta compute what f prime is for the Newton's method.
That's a rational. That's a rational equation.
So we'll continue on this next time. If you are stuck right now what to think about it, we can talk about it briefly so you can think about it. Do you need problem?